Let's start on lecture 14. We're going to look at jump instructions and loop instructions. Just a very quick review. For comparison instruction, we do D minus S, and we assume those are signed numbers, and the result will be three scenarios depending on the relationship between D and S. If they are equal, the zero flag will be 1, and if D is less than S, the zero flag will be 0, and the XOR on SF and OF will be a 1. And the third scenario is when D is greater than S. And we talked about condition codes. These are dynamics to imply certain flag conditions. It could be a combination of flag bits. We talked a little bit about conditional move, and we'll spend some time on set CCD, which is to set the byte to FF if the condition is true. Otherwise, the destination will be all zeros. And these set CC instructions can be used to build up complex conditions. Jump instruction is used to change the flow of a program. If without jump instruction, your program has to begin from instruction 1 all the way to the end, then there's a big limitation because you have limited program memory. In order to have a complex code or complex logics in your code, you have to spend an enormous amount of program memory if no branch instructions are available. This branch instruction will use its operand to specify which instruction should be the next one. For instructions other than branch instructions, the next instruction is very clear. Right? That's the one written right there behind it or below it. There are two general types of branch instructions: unconditional and conditional. For unconditional, it's JMP with a target. Target could take different format, and this unconditional instruction, jump instruction, always go to the address indicated by the target. On the other hand, conditional jump instructions, or JCC, takes one operand, the target, and the jump only occurs if condition is true. Note here this lowercase cc is one of the condition code. So you're going to replace the cc with a valid condition code. This slide shows you the difference between unconditional jump and conditional jump. On the left, that's the unconditional jump. So what we show here is the program memory, and we kind of divide the program instructions into part 1, part 2, part 3. And you can imagine that in this region, you have instructions stored one by one: addition, subtraction, compare, etc. And at the end of part 1, you have this jump AA. AA is the target. It could take different format. Here we use the label as an example. Label, let's say this is AA, which is the label of an instruction in part 3. So when the microprocessor executes this JMP instruction, no matter what you have after this instruction, well, no matter what instruction you have in part 2, this instruction will take the microprocessor's execution directly to this instruction here in part 3 because this label AA. In comparison, this JCC, or conditional jump instructions, has similar format, or exactly the same format as in this example. The target is AA, but in order for this microprocessor to go to this instruction here, it will have to check this condition. It only goes to this target address when the condition is met or the condition is true. If the condition is not true, it will execute the instruction immediately follows the jump CC. Jump targets. A target depends on distance from jump instruction itself. Remember that we talked about the code segment and IP instruction pointer. CS colon IP, this logical address, this combination, is actually the logical address of the current instruction. The microprocessor always uses the CS and IP, fetch the instruction, execute it, and then go to the next one. So the code segment, CS, is an important concept because that's where we're going to start with by defining intrasegment and intersegment. Intrasegment, that is to say the target or its target address is in the same segment. In other words, when the jump instruction goes to the target, if it does not change CS, code segment, that means the target address is in the same code segment as the jump instruction itself. So it is within this 64 kilobyte range. There's no need to change the value of CS in order to jump over that 64 kilobyte range. Well, in some cases, you do need that. And that's so-called intersegment. For this intrasegment jump, the target could be 8-bit or 16-bit immediate. So those are so-called short label or near label. You can use a label, any label, A, B, C, D, or any symbol to represent or to use as the label of an instruction. And depending on the location of that instruction, it could be a short label or near label. If it is very close to the jump instruction and you don't need to have a distance, well, the distance between the target address and the jump instruction, if it's within 256, that's within 8-bit byte range, then that's a short label. If it is a 16-bit range, then that's a near label. Also, the target could be a 16-bit register or memory location. In this case, the instruction pointer will be overwritten by the content of the memory register. Let me go back to the short label and near label. In those cases, this label, the offset, will be used to add to the IP so that it will get to the correct target address starting from the current address. For 16-bit register or memory, the IP will be overwritten by the contents of memory or the register. Example here, JEBX. JE is a conditional branch. This is to say it will jump to the target if equal. And the target is stored in the BX. BX is 16-bit register, and this 16-bit value in BX is the target address. You can also retrieve the target address from a memory location, like in this example, we do JE word pointer BX bracket. So that is to say, at memory location DS colon BX, we have a word, and that word is the target address. So the JE instruction will go to that memory location, fetch that word, and use that word as the IP, as the instruction pointer. For intersegment, that is to say the target is in a different segment. So it is beyond that 64 kilobyte range. That's the size of a segment. For intersegment, we have far label, or we can use a register, we can use a memory location. And in all cases, both CS and IP will change because that's how we get to another segment. CS will have a different value from the current jump instruction. Let's look at this example. We have 6 instructions here. CMP AX, BX, JE L1, this is a label, and we can see this is a short label because this instruction is only a few instructions away from this jump instruction. And although these instructions may take different number of bytes, but sure, this L1 and L2, these two labels, they are short label because these instructions are definitely within 256 byte range away from this jump instruction. And if you are given the initial values of AX and BX, what will be the final value in these two registers after these 6 instructions are completed? Okay, I'll give you 1 minute to work on this. So we'll look at the first case. Assume AX has 0010, BX has 0010. Then after that, you will look at the second case, assuming these different values in AX and BX. All right, first case, when both of these two registers have value 0010 hexadecimal. First instruction comparison, compare, we will do AX minus BX, and because they are equal, so the 0 flag will be set to 1. This JE, it will check the 0 flag. If it is equal, it will jump. It's indeed equal, so this jump instruction, this jump operation will be taken. So the microprocessor will jump to label 1. So that's this instruction. It will do subtraction AX comma 1. So AX will be a F. And then it will store the value in memory at DS100. So F, this value F will be stored in memory. The second case, when these two are not equal, the comparison will tell that AX is less than BX, so it's not equal. So this branch will not be taken. So this instruction will just be ignored. It will have no effect. And the next instruction is ADD. So AX will be incremented by 1. So AX will have 1, 2, 3, 5. The next instruction is JMP L2. JMP will be taken no matter what because it's unconditional. So it will jump to L2. As a result, the value, I think the comment here is incorrect. This should be 1, 2, 3, 5. Yeah. Right, it just copy over. And this is incorrect value here. There should be 1, 2, 3, 5 stored at this memory location.
Oh, that's a different problem. But when you check from the first part, that's correct. But the AX was BX, but nobody listen.
Yes, we're talking about the second case here. In the second case here, this is the incorrect value. This should be 1, 2, 3, 4, 5. Sorry about the confusion. Yeah, sorry, 1, 2, 3, 5. Yes, 1, 2, 3, 5. Right, this should be gone. This instruction at L1 will not be executed because this jump L2 skipped that. So we actually did a if then else. We actually check whether AX is BX or not, and based on the checking, based on the result, we will do different paths. Right? We will do either do the increment or do the decrement. So that's a if then else. And both parts have the same exit, which is L2. And that's where we store the value of AX into a memory location. Okay. So if then else, those are instructions at high level language. It's high level language, and the microprocessor doesn't understand it. So compilers will effectively translate that if then else structures into assembly languages structures like example we just saw. And then that assembly language instructions will be translated into machine code, and that's the actual code executed by the microprocessor. So the same logic structure, but at different language levels. The second example, we have 4 instructions: move, shift, decrement, and JNZ. JNZ is jump, not 0, and the target is L. Let's assume initially AX has a 1. What type of high-level program structure does this sequence demonstrate? You're right, it's a loop. How do we know that? We first move 5 into CL, so this is initially put 5 as the initial value of CL. We have this instruction SHL AX, comma 1. This is to shift. Okay. We're going to logical shift the value of AX to the left for 1 bit. So this will make AX as 2. And the next instruction is decrement. We're going to decrement CL, so 5 will become 4. And then we do a conditional branch. And the condition is NZ, that is to check whether this decrement is 0 or not. Because CL is 4, so it's not 0, it will jump to this back to this L, which begins the second iteration. We're going to shift again. So AX will become 4, and then we decrement again. This time 4 will be decremented by 1, so CL will be a 3. JNZ will jump. We'll jump back because CL is not a 0 yet. So we'll do this for the third iteration until CL is 1, and then we decrement 1, CL becomes 0, and this time this J and Z will not be taken, so we're gonna go through to the next instruction. So how many times this shift instruction will be activated? 5 times. Let's skip this one. Okay, block move program. What we see on this slide is, on the left we have so-called the flowchart. This flowchart gives you a illustration about what are the operations will be performed and what are the conditions that will be checked, whether there will be loop or not. So basically this illustrates the program, the microprocessor's execution path. And on the right, that's the actual implementation of this flowchart. We implement these operations using the actual assembly language instructions. So let's look at the flowchart. We first start from here. We establish data segment, source block, and destination block. We do all the initializations of addresses here. We then set up a counter and for the points to be moved. Then we go into this loop iteration. We move the next source pointer to the accumulator, and then we move the accumulator to the next destination point. These two are essentially doing the data transfer from one location, copying data to another location. And then after that, we will update the counter and source pointer destination pointers so that we move on to the next data block or data item. At the end of the loop iteration, we'll check whether all the points are moved or not. If not, we'll go back to do another iteration, another move. If we figure out all the points are moved, then we stop. Looking at these instructions, we have move AX comma data segment, that's a constant number, and we initialize the data segment, and then we also initialize the source index register, destination index register. You will see that here we use SI and the DI as the effective address. So that's where we'll find the data, and that's where we're going to store the data. We also initialize the counter register CX to be N, and it could be 100 or it could be 1,000. So in the loop iteration, the first move will copy first move is move AH, comma, SI. And the second move is move, comma, bracket DI, comma, AH. If I draw the memory map, so within the data segment, we have DS colon SI, and we have DS colon DI, and we have some words. And we have register AH. First move instruction will copy the value to AH. And second move instruction will copy the value to destination. And then we're going to increment SI. So SI will be now here, and DI will be now here. And then we check whether CX is 0 now. First time iteration, CX is definitely not a 0, so the J and Z will come back to the first move instruction. So we'll move this again to here, and then copy to the next location. So it depends on the value of N, you will do these many copies. loop instructions. From the previous example, we see that if we want to do a loop, we need to initialize the counter, we need to check the condition, and we'll do counter decrement counter. Loop instruction combines all these into one operation. It uses CX as the counter register. And it'll decrement CX register, then check if CX is 0 or not. The target must be a short label. So the format is loop target. It will go to target if CX is not 0. Also, there are two other kinds, loop E or loop Z. It will go to target if CX is not a 0 and the 0 flag is a 1. And this is the other opposite variant. So let's look at this example here. Well, this is the general structure. You move CX, comma count. So you can initialize the value, and you're going to start the loop iteration, and you do loop next. So loop will do the decrementing and also the checking using this one instruction. This is the same example, okay? The block movement. What we changed here is just this loop next pointer. Initial implementation, we have decrement, CX, and then we do the J and V. So here we just use one instruction, loop. So if we want to rewrite this example that we saw earlier, we can use loop instruction to combine the last two instructions, decrement and J and Z. So what will be the new instruction? The loop instruction we use in this example. It will be that simple, just loop L. Just use loop with the target, and target is L, the label here. We have another loop example. You can, this is actually example from the textbook. I think I'll leave it to you as the home exercise, not a homework. You can just practice to work on this example. And that's all for today's lecture.